So now we're starting to look at BLAST. BLAST is actually local alignment. So it's the slightly different version of the algorithm where you not try to match the complete sequence, but you actually look at the subpart of the sequence that has an optimal alignment. And in the case of proteins, which is also what you're going to use BLAST for in the practicals, that really makes most sense, because typically a smaller evolutionary units, also called domains, you'll see that in next lectures, that actually are conserved during evolution. Okay, so we'll look at BLAST. We look at the algorithm of it, and we also quickly look at SciBLAST, which is something very specific for protein sequence searches. And in theory, it should be way more sensitive than BLAST to find sequences that are not very similar. So if you have sequences that have the bars very far away from each other, so you maybe look at a similar gene between us and zebrafish or something, and so you look at something that's really far away, then SciBLAST should be easier to, or should be better at recognizing the similarity between those proteins than just a simple BLAST. We'll see that later. Okay, so BLAST is actually, as I said, one of the most used algorithms in bioinformatics, and it's not only used by itself, it's also used in many other workflows. So typically BLAST is just one of the many steps where you start with, and you'll see in some of the next lectures that BLAST also now is used on a very high scale almost everywhere. And it's so important because, of course, the evolution of the sequences and therefore also of the DNA, for example, that we try to analyze later, is all in the sequence evolution. So if we want to know, for example, similar functions of two genes, we typically can infer a function. So we say we've done an experiment on E. coli or zebrafish, and we want to infer the same function for humans. We already make a really good guess if we have a protein that has a very high sequence similarity. So often we can infer biological function actually through the sequence similarity. Now this is not a one-on-one, and it's also something you will see later on when you do benchmark yourself. But that's why it's used so much. Has over 60,000 citations, still being cited lots also currently, so it's not something that's trading off. And there is also faster forms of BLAST, and also the algorithm that's used nowadays a lot to, for example, analyze DNA sequences of patients coming out. It's not directly BLAST, but a lot of them are based on very similar methodology as BLAST. Alright, so similar overview as we saw earlier. BLAST is actually different, or is more than simply local pairwise alignment. So it's based on local pairwise alignment, but it has a higher aim. In fact, it's a basic local alignment search tool, and it's the search tool here that actually makes a real difference in the algorithm. So what's BLAST used for? You have one sequence, and probably most of you have run it before. You have one sequence against a huge database, typically even just all the sequences that are available. This is gigabytes large at the moment, millions of sequences. And you want to know which sequences in your big database are similar to your favorite sequence. Yeah, this is the typical question. So it's a huge search, and you don't want to make the sequence alignment wrong, but you need to make it a lot of times. And in the worst case scenario, so this is the simple algorithm. If you had to come up with it, maybe if you had to do it right now, you'd maybe think to fill in this dynamic programming for every single sequence in your database. And then we can wait for a long time. The sequence database is available today, so that's not actually what's done, and so what BLAST is actually a shortcut. So what goes in? A query sequence goes in. We start with the database full of sequences, and just as with the alignment we saw earlier, we need parameters for the alignment. So typically you would have a substitution matrix, you have gap penalties. BLAST also has some other parameters, and it's a good idea to have a look at those, because it really makes a big difference how it runs. So you have something called word size, which is usually set. You also have a significance threshold. This specifically makes a big difference if you run side blast. Then for the outputs, you actually get a lot of hits, and hits are actually high scoring regions or fragment pairs from your database. So a fragment that scores highly, gives a high score for the alignment between your query sequence and a hit in database. So you actually get the alignment back, you get a bit score back, which is very similar to the slightly normalized form of the type of alignment score we just saw, we just generated, and then from the alignment score, a statistical value, and the most one for BLAST is used an e-value, is generated to give you an idea of how likely it is that you found that match. Alright, so in pictures, this is what it looks like. You start with a query, you have a huge database, you search through it, and from this database you get hits. So typically, BLAST orders them for you by e-values. You look at the e-value. It's quite simple to interpret it, and you decide the thresholds, and you take as the true positives the hits that have a lower e-value than your threshold. And so we see this picture later back. This is also the start of side blast, but then you'll see that we'll do some more there. So indeed, so how would we solve this problem? And given a database of within 1 million sequences. So assuming that for very bad hits, for things that are very likely to actually have any sequence similarity, how would you start searching for this? How would you, so you have this huge amount of sequences, what would you do?
Break it up in smaller pieces.
Break it up in smaller pieces. And then?
See one of those pieces online and search those
So
locations.
yeah, so this is roughly correct. So you would split up your query sequence, but also the ones in the database, and you can do that once for every search you have to do afterwards. So that's also something that's called compiling a database. So we split this up indeed in very small fragments. For proteins, as small as 3, so you get 3-letter words, they call it. And then you look at similarities between your query and your database hits. And so when would you then make a full alignment?
Start sticking the pieces together and see if you can find some constant alignments in there.
Yeah, so you could do it if you have one word match. Now for an exact word match for amino acids may not be such a good idea, because we just saw that actually some substitutions, if it's just in a similar amino acid, they're still very likely. So that may not be the best idea, and actually BLAST has done some more clever ways of going around that. But essentially this is the idea. So you cut it up in smaller pieces, and then you do matching per word between the query and all the database ones. And only if you have a significant enough match, and that this is of course a heuristic, you will actually proceed with the full alignment. Now here someone asked earlier, is this an exact or a heuristic method? Here the heuristics come in. So here you make an ad hoc decision that we're not going to try every possible sequence. So it could be that there's just no exact 3-letter word, but the sequences are extremely similar. So you may actually miss some hits in this way. If you set the parameters sensitive enough, now you won't. So there's always a bit of trade-off here between speed and missing hits. Okay. So this is indeed a heuristic program now. We have different versions, FastCap, BLAST, PsyBLAST, and also now, and we'll see this more towards the end of the course, and definitely in the next course, algorithms and sequence analysis, we also have for something called hidden Markov models, which are way more advanced methods to do sequence alignment. They're also more sensitive. But within BLAST, still this dynamic programming algorithm, which you just all did, that's called dynamic programming, is used to extend these alignments. So here you see the kind of overall global scheme of what BLAST does. So you have your query, you have your sequence database, You split this into words. Actually, for the sequence database, you only have to do this once. So if you have to run a lot of queries, you compile your database one time. This takes quite a while. But then once it's been compiled, it's very easy to do a lot of different queries because all the sequences in your database have been split in words already. And not only are they split in words, they've also got a structure, so that's actually easy to find the words back once you're looking for them. So then you have a BLAST database, so it's a very specific sequence database. Now we have a query and we try to match it. So we try to match words, and then we extend the match. So that means then at that moment we're going back to dynamic programming. We have this alignment matrix as you just saw, and we try to extend the match from the words onwards. Then for every possible data sequence that has a good enough word match, and then also the threshold here has a good enough local alignment, you generate a full alignment, then a bit score is calculated, and then finally an e-value is calculated. So as I said, typical output would not be a single alignment, but a whole list of alignments for sequences in your database that are similar to your query. And it's of course the matching words here, that's really the trick of BLAST. It's different from normal dynamic programming, and which is the key ingredient to speeding it up so much. We'll see later that this idea of splitting up in small words for DNA sequences in DNA elements is actually called gamers, but the idea is the same. And it also is used in other sequence alignment algorithms if we want to be even fast. Alright. So if you go through the steps in slightly more detail, so you have a query sequence, you would split this up into, for amino acids, in 3-letter words. So you get all these, and you see that we also take overlapping windows. So we also say this is sliding window. So first you get the window or the word QLN, but then you start at LNF again. So we do actually each word possible here. So we don't just have it up like 3 here and 3 here and 3 here, but we go to every possibility. Now we do a little bit more, so we actually start scoring these words, and we actually start scoring them with every possible other word. So you can imagine that you can make a library with all possible 3-letter combinations, and from that library you can then calculate a matching score with the word you're currently looking at. Yeah, so for example, now looking at GFC, you can actually generate a list of all the words that are similar to GFC. And similar, we have to define. We define it actually very much the same as we did that earlier. We use Blossom 62, so we use a scoring matrix, and we can now calculate the matches between GFC. So here we just take the middle, the diagonal substitution scores from the Blossom matrix. But for example, here we would look up the for GFC and GPC, you'd have to look up the substitution score for for phenylalanine into a proline here. And so you see that this score is also slightly lower than the exact matching word. Now then there's a cutoff for proteins typically at 11. That's a bit arbitrary, but that's been tested to be sensitive enough. So that's benchmarked. And then you see that everything, so all the words that fall below that threshold, you don't take into account. So now we have a whole list, for every word we have a whole list of words that are similar, and those are the possible starting points in the database we're going to look for. So we have 3 letters. For DNA we have 16, sometimes also slightly smaller letter combinations. And so these are, so why do we have a smaller word size for protein code than for DNA? Is that clear to everyone?
There are more amino acids.
There are more amino acids, right? So the number of possibilities, the number of possible sequences you can make with a 3-letter DNA is much smaller than with 3 letters amino acids, right? With different power in there. So that's why to have the same specificity, so the same chance of matching, you need a much larger a sequence or word in DNA compared to the protein sequence. Okay, so that's the first step, and we do that both for the query and the database. We pre-compile, we match words, we have a sliding window of a sequence to generate all these words, and we scan for exact matches, and then also for things above this threshold. So now what we want to do is we want to extend the match. So the idea is simple here. So say here we start with a match. We have two sequences, the query and the wanted database sequences. We have in this position here we have a word that matches, and now we actually can extend the dynamic programming matrix in both directions. Note that the axes here are flipped compared to the matrix you've just been. So what is diagonal here was on this part here was actually diagonal in this direction. Yeah? So you start extending it. So here means that you generate the alignment, go to the left or to the bottom. Also here to the left means that you or to the top means you start having gaps, right? So the further away you get from this diagonal, the more gaps you've introduced in your local alignments. And here, because it's a local alignment, you can actually stop once your score is going down again. So you don't actually have to necessarily fill in the entire matrix. Now, this is the original version of BLAST. Then a second version of BLAST appeared, which is gap BLAST, or the two-bit extension method. And there it's actually looked for two matches in a sequence, but the threshold for the word similarity could actually be lowered a bit. That means that in practice we can look for sequences that are slightly more diverged, because they don't have an exact word necessarily matching anymore, but they have at least two very similar words in a close vicinity, and then we start matching. So what's done then is given some cutoffs, you look at two words, and if they're on or roughly on the diagonal, we actually start extending the hit as before. So now we need actually two matches with a slightly lower threshold. Alright, so that's two hit methods. Now, then you generate the alignments. We've roughly seen before how that's being generated. Here's some text for that. And then, maybe the very important part is the scoring function. So now we have a score, but for a lot of the alignments, we'll get out some kind of positive score. So just having a positive score and having a small local thing doesn't necessarily mean that evolutionary these two proteins are also really related or that they have the same function. So it doesn't necessarily mean that having a score that's positive or maybe above 10 or something is also therefore significant in terms of biology. So that means we need to see how likely it is that if you have two completely random sequences that we align, how likely it is to get a similar score. And so we get these scores simply from the highest point in the dynamic programming matrix. Slightly different from here. So before we looked at the end position, but for local alignments, we look at the highest score to get the first score. Now this is transformed, so this score here from the alignment matrix is first transported to a bit score, and then later transferred to the e-value. And so an e-value is quite intuitive. You can rationalize about it. And it also immediately has the concept of the database in there. So of course, the larger your database gets, the more likely it is that you also find random hits in that database. Yeah, so an e-value is the expected number of non-homologous sequences with a score greater or than a score x in a data set of sequences. So what we do is we generate this bit score, this alignment score for a hit, and then the e-value corresponds to how likely it is that we would have found a similar scoring sequence in a random sequence database by chance. And so typical values for a good equal would be something like 0.01 or 0.001. So 10 to the minus 2, 10 to the minus 3. That are the typical thresholds that are used. And that's also given the database. in your project will actually ramp up the e-values a bit. So you will actually even want to include e-values of about 5 or maybe even up to 100. So they are really insignificant hits, but that's to benchmark it. So you want to see how sensitive it becomes, even if we take bad things into account. You'll see that later, but remember that you may actually, for your project, may want to, at the later stage, want to keep higher e-values to generate one of these nice benchmark curves. Alright, so back to our quest to actually generate this e-value. So now we know what we want. We want an e-value, we want something that indicates how likely it is, but how do we actually get to this? Now, the nice thing is that the extreme value distribution, so this is a well-known distribution, there's good references for that as well, the Wikipedia page, approximates the distribution of sequences, of the expected distribution of sequences that are randomly aligned quite well. So I'll go over that one more time. So here in red we have the extreme value distribution. So this is a distribution, so the peak means that most of the scores of a given sequence length, most of the scores will have a value around 40 to 50. Yeah, that's the peak here. Yeah, and so there's also some scores that score way higher. So this will be your random bulk, and here will be the significance sequences right at the end. Yeah. So these were the high scores. Now in blue crosses, we actually see what happens if you have a sequence, take a query sequence, and then you have a database of random sequences. Maybe you, for example, try this against a sequence database where all these sequences are backwards. Yeah? So they don't have any biological meaning, but they're a random set of sequences. And so this is the distribution of blast scores you would get in that case. And you see that the extreme value distribution is quite a good approximation. And actually, you can write the red line down in an equation, and that's what's done here. And then you can actually estimate the M and the N are the sequence length of the query and the database, and the K and the lambda are now parameters that you can actually fit. So what's done is that we can actually literally make a fit to this function here, and then we can estimate these parameters K and lambda. Now we need to transform this, so approximately your expected number is actually this E here from this extreme value distribution times your database size, where your database size you may actually also take the query sequence into account. So finally you can then calculate an E-value like this, taking this formula, which is basically fitted, and then we can see for a given score, which is this S that goes here. This S is the score of the alignments. Taking that into account, we can actually process that to get an E-value for each hit that we found in the database. And so then we can assess if it's indeed very likely or unlikely that this is a true homolog or has significant sequence similarity. Right, so this is the end, so we have the score and we transform the bit score into an E-value. And then we have all our outputs. Okay, so just to come back to the project. So I already mentioned something. Why would you actually run BLAST? Any ideas? Who has run BLAST before? Oh, that's surprisingly few. Okay, so why did you run BLAST?
We need to find out if my sequence carries any mutations or not.
Okay, so you wanted to mutations, but with respect to something else then, presumably, right? So you want to, exactly, so you first want to find a reference, and then you want to see, for example, so this is a really good reason, it's not actually one I wrote down here perhaps yet. So you have two sequences, you align them, and then you actually see where the sequence is most conserved. So on the places where you have mutations, it's less conserved. But sometimes, if you, for example, have two proteins with two different functions, actually the mutations can be really interesting as well, because where the differences are may actually be the difference in the function. So there's two ways of looking at it. So we can look at the evolution to see where significant or insignificant changes are taking place. Anything else?
Identification of certain microorganisms.
Yes. So for example, if you have metagenomics data, so you have a microbiome sample or something, and we can sequence that nowadays, and we get actually many sequences, gene sequences, like usually have part of it, that we don't even have the full genome of that bacterial species. We can still try and match it, translate it to an amino acid sequence on a protein database, and then have an idea what functions are present in that microbiome samples. But that's indeed very. Anything else?
For finding orthologs?
For finding orthologs, yes. So finding similar functional genes in a different species. Anything else?
For structural prediction,
Yes.
we use protein A negatively.
Yeah. So indeed, so we'll see also later in one of the later lectures, if you have similar structures, typically the sequences are also similar. So we can turn it around, and that means that if you have two sequences that are significantly similar, it's very, very likely that the structure of the two proteins are also the same. Anything else?
Or primer design.
Yes, so you want to literally have matching sequences. Now we may actually not want too many gaps, so we're typically looking for really tight sequences. So you can still use BLAST. Yeah? Anyone? I think actually maybe most, or at least the original motion is actually to find a function. So it's very close to finding an ortholog idea. We have a new sequence, we have no idea what it's doing. We try and blast it to the nearest head that has at least some annotations or some experiments done on that protein, or maybe has a structure, so we know more about the protein. Alright, so quite a lot of different reasons, and actually you'll see later also that these databases match what you may do. So this is sequence structure, this is what we just discussed. So typically, if the structure is the same, the sequences have a little bit diverged. But typically structure and function are more conserved than sequence. So if we have the same sequence, it's very likely the proteins still have the same structure and also a very similar function. But we also have a big problem. Because structure and function are typically more conserved than the sequence itself, the sensitivity of something like BLAST isn't actually high enough, not as much as we would like. So if you just use BLAST, you can detect kind of this blue region, so we've a more number of residues aligned, you get a higher score, so we come in the significant region, or if we have a higher percentage sequence identity, so this is what we can detect. There's a whole region here of red where we still have similarity, we still have functional and structural similarity, but we can't actually detect it with something like BLAST. So there's a big gap here. So there's a lot of work to kind of try and dive deeper into this red zone. And I think one of the later lectures have a slide, and you see that only about 20 to 30% of the true structural similarity and functional similarity can be found by something like BLAST. And the rest is completely noise, as in the random, so it will fall in your random peak of similarity. Alright, so this is why the first method that really is more sensitive is PsyBLAST, and it's very similar. It's actually just BLAST but run a couple of times. So it's an iterative BLAST, so we don't run it once, but we run BLAST multiple times. It takes longer, so it's more computation, more expensive. And it works as follows. So the real key idea is that we use evolution here. So we look at the positions in the sequence that are more conserved. So we run BLAST once, and then we generate a lot of hits from that first run. And then we can generate an alignment. In this case, we can take our sequence, we can align, just like here, all the other sequences below it, and we can look at each position, each sequence position, and we can see which sequence positions have remained the same in the other sequence, in the related or the homologous sequences. And those positions apparently are more conserved. So if you want to do a next run, you can actually put more weight on those positions that are conserved, and then search the database again. Yeah, so we're using here evolution itself. We're looking at closely similar sequences, and then look at the pattern of conservation and say, okay, apparently these regions are very conserved. They were important for the protein, so we need to put more weight on them, and then you can find way more sequences. And then you can iterate this process, because then you run BLAST again, and of course you can keep doing this. So in a scheme it would look something like this. So you have your query database, this is just BLAST. We run it against the database, we generate hits from this. Now this threshold becomes really important, because what we don't want to do is in this conservation pattern include loads of false hits, right? So we really want to be quite strict and say like, well, we only really want to take true hits into account. So this is the red line there. Now if we go to PsyBlast, so we only take the hits that give me thresholds, and then we generate this position-specific scoring matrix. And then using this position-specific scoring matrix, so not the query itself, but the position-specific scoring matrix, we run that again on the BLAST database. Yeah? And so now you get new hits out. You get, if you're lucky, you get more hits out. And so you can do this again. You have now a longer list. From that new list, you generate a new PSSM, and you can run that again on the database. So typical runs can even iterate this 5 to 10 times to get very sensitive searches. So this is the same, the query, you have your hits, and they're aligned to your thresholds. And then you look at which positions, so these are now hits, database hits, and you look which positions are aligned and which are conserved mostly. And on those you will put more weight. Then you get something like a position, sequence position scoring matrix. So here is the sequence positions of your query. So this on this diagonal here, this is as long as your query is, so much longer than 8. You typically have 200-300 positions in the matrix there. And here you just have the 20 amino acids. And then for each position and amino acid combination, we say how likely is it to find that type of amino acids on this specific position. Yeah, and then we put a log over that, and that log gives you then something very similar to a BLOSUM matrix. Apart from that, we now have not a 20 by 20 table, but we have a sequence length 10 times 20 table. And once we start aligning, we actually use these substitution scores to generate the alignment. So it works very similar, but it's different in that you get so we don't have the same substitution matrix for every single position, but actually depending on the position we are in the sequence, we get a different score. And that way it means we can put more weights. If we see that this position here is always a cysteine, you'd get a very high score for cysteine here and very negative for any of the other amino acids. Is there a question?
Yeah, so you're saying it's like repetitive, basically. But I'm getting at, can I change the algorithm parameters to kind of, like let's say maybe change the word length at the beginning? I would use like 10, and then that, like since I have like a already a base score, can I extend that or?
Yeah, so once you're doing the benchmarking, you're certainly allowed to play around with the parameters. I would even advise you to do so. I think we have not so much time left, so I'll just quickly go through the last couple of slides. But yes, I would definitely try some things out. So here you get the sequence, the sequence is the same thing. This is your PSSM, and then you use that. So here you can see the conversion from counts in the first place or frequencies to then locked p-values or BLOSUM values. One of the other things that's used in BLAST a lot is low complexity scoring. You see that as an option as well. So you see sometimes you get sequences that have here, so PPP, CPP, so it's very repetitive. Now, it's very easy to match a sequence like this, but it's typically not evolutionary significance. So typically BLAST actually filters these out and doesn't match. You can, but if you think it's important, actually looking for this type of rigidity, you need to switch it back on. So it's an important parameter. One of the other things you should consider if you do PsyBlast is that the threshold becomes extremely important. And once we maybe have the threshold too lenient, you may actually also get a lot of worse in benchmarking performance. So we may actually see that if we make a PSSM of sequences that are not actually evolutionary related, we actually start looking for the wrong thing. And so you will actually see that your log curve becomes worse if you put the threshold for inclusion into the PSSM too lenient. All right. So you take home. The Needle algorithm is something you definitely need to know. So the global alignment parts, you should roughly know how the BLAST alignment works and what the different parameters mean. You will also see that in the practical again. Maybe just before you go, just before you go, this is one thing that most people do wrong in the benchmark later on, or at least. So what do you think is very important here if you have this database? Say you do this over a small database or a very large database. When would you get the better SciBlast results? The very large one, right? So this is different from BLAST because it doesn't actually reuse the other sequences in the database again. So say we're only specific in genes from the mouse, but we want to do a human mouse search, but we think there may be some very big changes in some of the genes. Then we would not just compile a mouse database to run BLAST over. You'd actually use NR, entire set of sequences, generate a SciBlast profile, so a PSSM over that, and then with the PSSM, search only the mouse. Yeah, because only then you get a very sensitive PSSM. Well, that's very important, and I'll come back to that later. But the database, what's in the database, is actually very important for your final output and your sensitivity of SciBlast.